together. So the first one, oh shoot, this is a parabola though. Shoot. I don't really want to do a parabola application. I thought it was an ellipse, but it's a parabola. Okay, I'm skipping to number 7. So a whispering gallery, it has an elliptical ceiling. So here's the ceiling of your whispering gallery. And it says, so this is like half of an ellipse, right? So if you've ever seen a whispering gallery, if you stand on one of the focal points on the floor, basically what happens is the sound bounces off the ceiling and goes directly to the other focal point, because remember, the distance, when you add together, the distance between the two foci will always be the same. So like if it bounces off here, it's going to go directly to that focal point. If it bounces off over here, it's going to go directly to that focal point. So if you stand on those two focal points, you can literally whisper and the sound will bounce off and go directly to that other focal point. So it says the foci are located 15 feet from the center on the floor. So here's the center. So they're each located 15 feet from the center. So that's your C value for your ellipse, right? Because the distance from the center to the focus is C. And it says the highest point of the ceiling is 20 feet. So this distance is 20 feet, and that would be the B value of the ellipse. So they want to know how long the whispering gallery is. The whispering gallery has a length of 2A, right? So if I can figure out A, the total length would be 2A. So I don't even really need to make an equation. I need to use the a squared equals b squared plus c squared relationship for an ellipse to figure out A. So now that you know what B and C are, I'd like you to plug them in and see if you can solve for what A is, and then we want the total distance, which is 2 times that value. So grab a calculator and try that one. All right. So I ended up getting 25 as A because I took the square root of 625 and then 50 as the total length. Does that make sense? So just orienting a picture with an ellipse. So after I go through a couple applications with you, those who have done everything else, I'm going to have you go back and like graph the parabola on this page for practice. And there's one graphing a hyperbola, putting this ellipse into conics form and graphing it. I forgot to put the graph here. I guess it didn't print. And then there's one more ellipse, and you want to find the eccentricity. Oh, there's my graph. It snuck on the other page and got cut off. That's why. So graph an ellipse, graph a circle. So those of you who have done everything else in a minute are going to go back and finish 904 as your review. But I'd like to take a look at that number, page 408, number 20, 21, and 22. Because these are all ellipse applications that I want you to be comfortable doing. So they were on the 408 review. And those of you who still haven't done 408, I want you to finish that so you get checked off for this virtual work. So 904 is not getting checked off, but 408 was checked off, so you could go back and work on 408. I just want you to do some review today to help you prepare for tomorrow. So looking at number 20, planet McCracken, here it is, travels around the sun in an elliptical orbit, and the sun is at one focus. So here's your two foci, right? So if you drew this in, here's your center, here's your two foci, but the sun stays put and the planet circles or orbits around it. So it says the minor and major axes of the orbit have lengths of 250,000 kilometers and 300,000 kilometers respectively. Now it doesn't really matter if we orient it vertically or horizontally, just major is going to be longer. So to me, this looks like the way it was oriented on the paper, the major axis is the longer one. It happens to be horizontal. Find the greatest and smallest distances, which are called the apogee and perigee, from the sun center to the planet center. Both of these distances are found using the major axis only. So I just want to show you what it's going to look like when it's at apogee. So the sun always stays here. So when the planet is at that point, it's the closest it's ever going to get to the sun. And when the planet is, so the sun stays here, when the planet's over here, it's the furthest away, whoops, it's going to get from the sun. The values don't change a lot. So for the Earth, for example, we stay pretty consistent in our distance to the sun. So we don't notice a big change when we're at apogee or perigee. But a planet like Pluto swings way out there. So it has more extreme distances from the sun during its orbit than we do, because we're closer and we're more circular of an orbit. So we want to figure out what this distance is and what this distance is. I want to know the furthest and closest that I am to the sun. So the information they've given me is that the major axis, the total length is 300,000 kilometers. How can I use that to solve for A? What would A be for this planet? I need to solve for A, B, and C because this distance right here is A, and this distance right here is C. So if I take A and subtract C, aren't I going to get that missing distance that I'm interested in? And likewise over here, this distance is A and this distance is C. So if I add together A plus C, then I'll have this total distance that I'm interested in. So I need to solve for A, B, and C. So what would A have to be in this case? It says the total major axis is 300,000 kilometers. This is the total major axis, right? So what does A have to be? Half of that, right? 150,000. So A is 150,000. We know that B is going to be half of 250,000. So 125,000. So to solve for C, you're going to do that Pythagorean identity. A squared equals B squared plus C squared again. So 150,000, I would store all this kind of on your calculator. Don't write these huge numbers down. Plus C squared. So you're going to have to square A, subtract off B squared to the other side, and then take the square root. So you should be able to do that all on your calculator. And once you have C, you should be able to answer the question, because I said on one of them, you take A and subtract off C, and on the other one, you take A and you add C. So you should be able to finish that problem now. Did we get the same answers? Can you check this? I got 82,000 for C. So my perigee, which is the closest, was 67,000 kilometers. And my largest apogee was 232,000 kilometers. I didn't say the end of the number, but we got the same answer. So figuring out where A, B, and C are on the graph is important for answering the question and using that Pythagorean identity. So take a minute. If you haven't done 21 yet, I'd like you to try that one on your own. And then I'll come back in a minute and show you the answer to 21, and then we'll do 22 together. And if you're waiting for me, go to 904 and do those couple problems. Correct? So I said that A by itself, if the whole length is 120, A is 60, so I put 60 squared in as A squared. 18 is C, so 18 squared. I subtracted it and took the square root. So the height would have to be 57.2. Does that sound like what you got? So again, manipulating A, B, and C is kind of the big idea for ellipses, other than just graphing it. So number 22, let's do it together if you haven't done it, because it's a little bit different than the other problems. So this is now an arch of a bridge over a highway, is semi-elliptical in shape. It spans 50 feet across. So here's my elliptical arch of a bridge. So it spans 50 feet. And the highest point is 22 feet. So that's the height of the bridge. So we've got kind of A and B values floating around. Write an equation for the ellipse in this situation. I'm going to center this ellipse at 0, 0 just to make it easier. So I'm going to make this x squared plus y squared equals 1. And that way all I have to fill in is the A value and the B value. or a squared and b squared. So it looks like it's longer in this direction because a is just 25, half of 50. So it looks like the 25 squared is going to go under x. So 25 squared again was 625, I think, right? So 625. And then I'm going to square 22 and put that under the y. So that would be 484. So now that I have an equation for the ellipse, now I can do something with it. So it says a truck is carrying an oversized rectangular cargo and it's 3 feet wide and 19 feet tall. Can the truck stay on its half of the roadway and clear the tunnel? So imagine here's your archway, right? The bridge, the truck, I mean, has to stay on its half of the roadway. So 3 feet out, what it wants to know, what is the height of the bridge? If the height of the bridge here or archway is 19 feet, it's going to clear it. But 3 feet out, if it's less than 19 feet, it's going to crash and hit up the bridge. So you know when they say clearance of a tunnel, you really need to look at the clearance way out here at the edge of the lane, not the height of the archway. All right, so what we're going to do is we're going to plug in 3 for x in the original equation and solve for y, because that would be the height of the tunnel. So we would plug in 3 squared over 625 plus y squared over 484 equals 1 to see what we're going to get. So to solve this, this is just a number. So it's the fraction 9 over 625. So we're going to take 1, subtract 9 over 625. And that's going to be kind of a crummy number on our calculator. So just keep it on your calculator. So now I have y squared, actually it's not that bad, y squared over 484 equals 0.9856 as a decimal. So what would I do next to solve for y squared? I want to get this 484 out of the denominator, so I would multiply both sides of the equation by 484. And that will give me y squared, so then I can take the square root of the answer to just get y by itself. So times 484, and then take the square root. So if you're bigger than 19, you're good, and if you're less than 19, then it won't make the clearance. So what would you say for your conclusion? I got that y was 21.8 feet. So yes, it will clear, right? Because it only needed to be 19 feet to make it under the tunnel. All right.